Now we will attempt question number 60. In this question we are given a triangular block like this of mass capital M, on which is placed a block, another block of mass small m, which is, that is, the system is kept on a frictionless floor like this. In addition, the friction between the two blocks, that is between small m and capital M, is also assumed to be 0. Now when you release the system in this position, what's going to happen is small m is going to travel downwards like this, and because on the system there is no net force in the rightward or in the leftward direction, that is the external force I'm talking about on the system in the horizontal direction is equal to 0. So naturally, if we take this as the x-axis and this as the y-axis, then we are confident that there is no change in the x component of the system's momentum. So delta px system is equal to 0. So what we are essentially saying is that the system's momentum is conserved, in the x direction. Just to clarify, we are not saying that the x component of the momentum of the individual blocks is conserved. That is, small m's momentum does change in the x direction. Similarly, capital M's momentum in the x direction also does change. All we are saying is that these changes of the x momentum of small m and capital M, although they are individually non-zero, they cancel each other. A better statement would be they individually could be non-zero. They could be non-zero, they could be 0. We are not sure at this stage. But if they are non-zero, then they must cancel each other. That is, the total momentum in the x direction must be conserved. Now let's put in some data. The question states that this distance, the height, is equal to h, and also this angle is equal to alpha. Now just suppose that capital M doesn't move and small m, it moves in this direction. This is not the case, but just as a step towards the solution, assume that capital M doesn't move. Now what's going to happen is, when small m reaches the bottom of the, that is over here, it reaches the foot of the hypotenuse, or the bottom point of the hypotenuse. Now by that time small m has acquired a velocity, some velocity in this direction, and we are interested in the x component of the velocity. So it has a rightward x component. Of course the y component is downwards. So what we can gather from this is, if capital M does not move, then small m acquires a horizontal momentum. No doubt it acquires a vertical momentum also, but we are concerned with the horizontal component. Acquires a horizontal momentum in the rightward direction, and therefore we may conclude that in order to counter this momentum, remember the initial x momentum, that is initial value of px for the system, that's equal to 0 because nothing is moving, and now all of a sudden you see that there is a momentum in the rightward direction. So to counter this, capital M has to acquire a velocity in the leftward direction. In other words, when small m moves down the inclined plane, which is the hypotenuse of the triangular wedge, the triangular wedge must simultaneously move towards the left. These motions happen simultaneously, the motion of small m and the motion of capital M. We will soon see in this solution that the motion of small m is a bit more complicated than the way that I have described. However, this is a very good starting point. Now what I'll do is I'll draw the picture when small m has reached the lowest point of the hypotenuse. So what's going to happen is, by that time capital M will travel to the left. So this is the ground, and capital M is, the left edge is somewhere over here. So that's capital M. This angle is alpha here. It's capital M, and the block small m is at this position. That's small m, and we want to find what is the velocity of capital M. That's the question. So let's assume that we know it's leftward, so we'll assume its leftward velocity is v1. Now let's come to small m. Small m has still not struck the ground. It's just about to strike the ground. So relative to capital M, it's moving with this velocity. That is, it is moving parallel to the hypotenuse with a velocity v relative, but as the suffix relative suggests, this is only the velocity of small m relative to capital M. So if you remember the relative velocity formula, v bar small m relative to capital M is the velocity of small m relative to the ground minus the velocity of capital M relative to the ground. Now in this picture is drawn with respect to the ground. So I really want to find the velocity of small m in the ground frame. I want this, and I want to show it in the picture. So I transpose this term over here, and what I get is the velocity of small m relative to the ground is the relative velocity which we have described in this picture. In other words, the relative velocity which was in this direction, and you have to add to it the velocity of capital M. That's capital M. So the velocity of capital M I already know, it is v1 in the leftward direction. So I'll just return to the picture and I'll add a velocity component towards the left. That's v1. It's the same velocity as this. So the velocity of small m related to the ground is the vector sum of this velocity and this velocity, and the velocity of capital M on the other hand relative to the ground is only this velocity. So if you look at this picture closely, you see that there is one unknown v relative and another unknown v1. This v1 and this v1 is the same, so there are totally two unknowns, and it would appear at this stage that we require two simultaneous equations to find these two unknowns. One of these equations can be got by applying momentum conservation in the x direction to the system. In other words, delta px system is equal to 0. So that means that px of the system finally is equal to px of the system initially, and of course this we know to be 0 because this is nothing is moving. So that's one of our equations, and later we will see that the conservation of energy will give us our second equation. But let's write this first equation, px system final. Now I have assumed that the x-axis is rightwards. I'll just draw it again in this picture. The y-axis is upwards. So let's first consider the x component of the momentum of capital M. Capital M is moving towards the left with a velocity v1, so its x momentum is going to be minus m multiplied by v1. The minus sign comes because it is moving leftwards. Now let's look at small m. The momentum of small m is given by m times, let's consider this component first. See, this angle is also going to be alpha. So what I can do is to find the x momentum of small m due to this velocity and this velocity separately and then add. What I mean to say is the following. Suppose I represent small m by this particle. It has some velocity which I'll call v2 bar, in this direction and some velocity v3 bar in this direction, and the total momentum is m into v2 bar plus v3 bar. Now I'm not going to try and add these vectorially. Rather what I'll do is I'll find mv2 bar and mv3 bar separately. I could do that. So the momentum of small m is the sum of these two momentum components, and when I am taking the x component of the momentum, I could take the x component of this and the x component of this separately and then add. So that's what I'm trying to do. I will find the two momentum components of small m. One of them is because of v relative, the other one is because of v1, and then add those x components to get small m's momentum along the x-axis. So let's consider the inclined velocity v relative first. It's going to be the momentum because of v relative in the x direction is going to be m times v relative, and I have to multiply by the cos of alpha because I'm considering the x component only, and it's positive because this momentum component is rightward. Now let's look at the other momentum component because of v1. It's leftward, so it's directly minus m times v1. So this is the total momentum of small m with respect to the ground along the positive x-axis. This is the momentum of capital M along the x-axis in the ground frame, and of course that must equal the initial momentum, which was equal to 0. So that's my first equation. Now of course, as stated earlier, we require a second equation, and we will look to the conservation of energy applied to the system for providing us that second equation. Now because there is no friction present, there are no dissipative forces, the total mechanical energy of the system is conserved. So we can say that delta Ke for the system plus delta Pe for the system is equal to 0. Now what does that give us? I think I'll just create some space over here and move these equations a bit higher. That's so that we can see the diagrams simultaneously, right? So I'll just bring this a bit down. Yes, now you can see the initial picture and the final picture, and let's see first of all the simpler term is delta Pe in this case. You know that the gravitational potential energy of capital M is not changing, it's not moving up or down, it is small m which is contributing towards delta Pe, and the change in its gravitational potential energy is negative. So I'll just write the equal to 0 on the right hand side, and this term is minus m g h. It has dropped by h. The assumption here is that small m doesn't have very large dimensions, it's a very small block, and that's why if you look at the diagram, small h is actually the height difference between this point and this point. Now really speaking, if we want to find the change in the potential energy of small m, you have to find by how much the Cm has dropped. So the Cm is over here initially, and by the time it reaches the ground, I'm assuming that small m is uniform, so the Cm is at the center, it's over here. You can see that the Cm of small m has not actually dropped by h, it has dropped by a bit smaller than h. Another way to see it is, you just take this particular edge of small m as the reference, and if that edge reaches this position, that is, it's just hypothetical, it can't do that, it's inside the ground, so if small m manages to reach that position, then of course we can say that the height difference is between this point and this point, that's h. The Cm as well as all particles of small m have dropped by h. Now that's not the case, the Cm has fallen by a bit smaller than h. So we are going to assume that small m is a it has a very small geometrical dimensions. The length, breadth, etc. are very small, length, breadth, height. So we can treat it as a particle situated at the top initially, and then it goes to the bottom, and that's why we write h directly over here. Now let's go to the delta Ke term. Look at capital M first. That's a simpler block. So the change in capital M's kinetic energy is the final minus the initial, as usual. Now the final kinetic energy is half capital M into V1 square, and the initial is 0, so minus 0. I'm not going to write that. So that takes care of capital M, plus the change in small m's kinetic energy. So let's see what is the final kinetic energy of small m. Small m's velocity in the second picture, its kinetic energy in the second picture is half m into its final speed, which is v, let's say, square. So you know that small m is going to actually travel with a velocity which is the vector sum of these two. So that's, I can call it v bar, let's say, somewhere in this direction, and the modulus of v bar is v, the speed of small m with respect to the ground. Now we know the velocity components of small m, but they are not in mutually perpendicular directions. So we'll have to go by the basic formula v mod of v bar, which I have called v, the speed, is equal to square root of v1 square plus v relative square plus 2v1 v relative times cos of the angle between them. I'm talking about this angle, and since this angle is alpha, this must be pi minus alpha, 180 degrees minus alpha, and of course this is going to be minus cos alpha, so I write cos alpha here and I change this to a minus sign. So that's mod v bar or v, and here I've got the square, so I square this, and I remove the root sign, and that's what I'm going to put over here. The final kinetic energy of small m in the ground frame is half m into this big thing, v1 square plus v relative square minus 2 into v1 into v relative into cos alpha. That's the kinetic energy finally of small m. The initial kinetic energy of small m is 0, so I don't write that, I should write minus 0, that is actually. So this is delta Ke of the system, this is delta Pe of the system, and their sum is equal to 0. So that's my second equation, and you can see I've got two equations in v1 and v relative. They are the only two unknowns, everything else is known, and we want to find v1. Now this job I leave for you to do. From these two equations, it will take a bit of complicated mathematics, I'm sure, but I'm also sure that you will be able to solve it. You have to eliminate v relative. You can retain cos alpha in the answer, that's not a problem because alpha is given. For that matter, you can have even sin alpha in the final answer, or you can have tan alpha also in the final answer. That's not going to matter, alpha is given. You can retain h in the final answer, that's okay, but you have to eliminate v relative. V relative should not remain in the answer because it's an unknown. So get rid of v relative from these two equations and finally get the answer for v1. That's how to solve this particular question. And of course there is one more question which I have added to this, an extra question related to the same problem, and that question is to find capital M's displacement in the leftward direction during this process which has been described. In other words, when small m reaches the base of capital M, we have just described that capital M is going to move towards the left. And you can even see I have drawn a reference line over here indicating the initial position of capital M, and this is the final position. You can see that capital M has moved leftward by some distance, so its leftward displacement I can say x1, and we have to find what is the value of x1. That's the extra question. Now if we consider the entire system, then the displacement of the Cm of the system in the x direction, so delta x Cm of the system, we have studied this earlier, that's the summation of each mass multiplied by the corresponding delta x of its Cm and divided by the total mass. In other words, the displacement of the Cm in the x direction is the mass weighted average displacement of each individual Cm. Now the Cm is originally at rest, and we also know that the external force acting on the system in the x direction, that's equal to 0. This we have already described in the in the first part of the solution. So there is no frictional force, for example, acting on capital M from the bottom. Now because of this, we know that the Cm's acceleration, we are talking about the x component of the acceleration of the Cm of system. Now that's equal to 0. Just apply Newton's second law. So sigma f is equal to ma in the x direction, and that means that the x velocity of the Cm of the system doesn't change from its original value of 0. Now if that is the case, then Vx of the Cm of the system is always equal to 0, and that means that the Cm of the system cannot get displaced in the horizontal or in the x direction at all, and that would mean that this particular delta x Cm of the system must necessarily be equal to 0, and if that's equal to 0, then the numerator over here is equal to 0. So the mass small m multiplied by delta x of the Cm of small m plus the mass capital M multiplied by delta x of the Cm of capital M must be equal to 0. Now let's write this term first. Remember, we have taken rightward as positive. I'll put in some symbols. Now this already I've used. X1 is the displacement of capital M in the leftward direction. Okay, I'll proceed with that symbol. So this is going to be minus m multiplied by x1, because x1 is towards the left, right? On the right hand side I've got equal to 0. Now this is going to be small m multiplied by, let's see what is the horizontal displacement of small m. You can split it into two parts. First of all, small m, it moves in this direction down the hypotenuse, and of course this angle is alpha, and the other displacement is towards the left because it moves along with capital M. Both these displacements of course take place simultaneously, and we are going to add them as vectors. Now what is the hypotenuse? The hypotenuse is going to be h divided by sine alpha. If you just solve this triangle, hypotenuse is h by sine alpha. So one of the displacements of the block small m is along the hypotenuse, and that's actually x relative. It's the relative displacement of small m, and it is relative to capital M, and at the same time small m moves towards the left along with capital M, and that displacement is of course x1. So what do we get? M into down the hypotenuse, the displacement is x relative, which is h by sine alpha, and of course I must take the component towards the right. H by sine alpha is not towards the right, it is inclined, so I must multiply by cos alpha, this angle, that is cos of alpha. That gives me the rightward component of x relative, minus, now x1 is towards the left, so minus x1, that's why it's minus. That is the what small m into delta xm reduces to. And now of course I just have to do some manipulation. I get m into h into cot alpha minus mx1 minus capital mx1 is equal to 0. I can take the x1 terms to the right hand side, so this becomes small mx1 plus this. Take x1 common, it's small m plus capital M, and finally what I get is x1 is equal to mh cot alpha divided by small m plus capital M. So this is the leftward displacement of capital M in this entire process.